What's up? This is Mario, and welcome to Awesome Acoustics. The purpose of this video is a little bit different from what I typically do, so I prefer to do it as a separate thing and not so much as part of my educational series. In this video, I want to talk about some strange beliefs regarding 432 Hz tuning. I am going to mention tuning systems, so if you want to understand the mathematical basis of different systems, I recommend to watch episode 3 of my educational series. There is a belief around the internet that 432 Hz is a healthier frequency for humans for a lot of spiritual reasons. Tuning to 432 Hz actually means tuning the note A4 to 432 Hz, and deriving the rest of the frequencies from there. This tuning is sometimes called Verdi tuning, but the discussion regarding this tuning is a very confusing topic, as there are several different tunings which are all called the same way. Sometimes, for example, when they speak of Verdi tuning, they refer to an A4 equals 432 Hz tuning with equal temperament. Sometimes they refer to C4 equals 256 Hz with equal temperament, although this is actually something called scientific tuning, as I'll explain in a few moments. Sometimes they speak of C4 equals 256 Hz with Pythagorean tuning, where consequently A4 gives 432 Hz. Sometimes they use other types of just intonation, which can even be arbitrary to get certain specific frequencies. But generally, Verdi tuning is associated with A4 equals 432 Hz. I think one reason for this confusion is that they typically do not specify the intonation. There can be many tunings with A4 equals 432 Hz, but with different intonations that give you different frequencies for the rest of the notes. As I mentioned a moment ago, the tuning called scientific tuning is based on C4 equals 256 Hz with equal temperament. This tuning is not used musically, but it has been used in some scientific papers for the convenience that all C notes are powers of 2. To tune in this way, we use this version of the formula for equal temperament. We have 256 here and 40 here, since C4 is the 40th key on an 88 key piano. I don't know of any engineer or scientist who actually uses this tuning, including myself. Naturally, we also stick to the standard A4 equals 440 Hz tuning when making music. A fascination with the number 256 is that it is an elegant number for being a power of 2, specifically 2 to the power of 8. However, if you calculate the frequencies with Pythagorean tuning based on A4 equals 432 Hz, C4 does not give you 256 Hz. Rather, you have to be based on C4 equals 256 Hz in order to get A4 equals 432 Hz. So, more than an A4 equals 432 Hz tuning, it is more correct to say that this is a C4 equals 256 Hz tuning. An argument in favor of 432 Hz, based purely on aesthetics, is the resonance patterns in water or in plates, sometimes known as cymatics. Basically, if you introduce vibration frequencies into a container with water or a plate with sand on top, the vibrations will form different shapes at different frequencies. This is true and can be calculated mathematically. However, one argument made by believers of 432 Hz is that some patterns are ugly because the frequencies are harmful, and other patterns are pretty because the frequencies are harmonious and healthy. First of all, this way of grading patterns as pretty or ugly is completely subjective. There is no objective standard or rating system to categorize the patterns as one thing or another. However, there is something more important than that, which is that the patterns do not depend only on the frequencies, but also on the dimensions of the surface, and the material through which the sound travels. I will now explain why this is relevant for resonance. When a wave travels through a medium and suddenly there is a termination or a change of material, the wave is reflected back. Some examples are a wave in a duct hitting a wall, or sound traveling through a metal bar and reaching the edge. Resonance occurs when the wavelength is 2 times one of the dimensions of the medium, or an exact fraction of that length. This applies to ducts that are open or closed at both ends. For a duct open at one end but closed at the other, the formula is slightly different, but we will not talk about that for now. Let's look at the example of a wavelength equal to half the length of the duct. To make the example clearer, I will show the reflections separately. When the wave is reflected a second time, the crests and troughs will coincide with the first wave that is still propagating. When two waves overlap in this way, the resulting wave has twice the amplitude. The same thing happens with the third reflection and the first reflection. Then, more reflections are going to be produced and superimposed, and the wave is going to keep reinforcing itself. This amplification of the sound field caused by reflections is what we call resonance. If we change to another wavelength that is not an exact fraction of 2L, the reflected waves do not coincide perfectly, and resonance does not occur. The same thing would happen if we keep the wavelength but change the length of the medium. When adding all the reflections, which will be more than I showed, the vibration will behave in this way. An important characteristic of resonance is that there will be points with very intense vibration, called antinodes, and points where there will be no vibration, called nodes. These vibration patterns, shown here in light gray, are called normal modes, and they are what explain the figures on plates with sand. Here, the black line will be the plate viewed from the side, which will be vibrating, and the orange circles will be grains of sand. The antinodes will be displacing the sand, which will be accumulating in the nodes. In water, vibrations can be seen with the naked eye. These are some resonance patterns for square and circular geometries. The more complicated patterns are formed at higher frequencies. During my master's in acoustic engineering, we did a laboratory exercise where we had a circular plate which we vibrated with an electrodynamic shaker at specific frequencies. First, we had to calculate its resonant frequencies mathematically and then find them experimentally. However, if the resonance depends on the ratio between the wavelength and the dimensions of the medium, this means that you can change the patterns not only by changing the frequency, but also by changing the dimensions of the surface where the sound is propagating. So by changing the size of the plate or the water container, you can get the good patterns with the bad frequencies, or the bad patterns with the good frequencies. Another thing that affects is the material. As I mentioned in the first episode of the educational series, the speed of sound is different in air, water, metal, etc. And the speed of sound changes the wavelength. So we also get different patterns if we introduce the vibrations to a different material, even if it is the same size and with the same frequency. Essentially, the frequency is not the relevant factor, but the ratio between the wavelength in the medium and the dimensions of the surface. Another argument they give in favor of tuning to 432 Hz is that it is more resonant with the planet, the universe, the water molecule, or various organs of the human body such as the brain or the heart. For example, they make the argument that the electromagnetic resonance of planet Earth is 8 Hz. And since 256 and 432 are multiples of 8, then this tuning resonates more harmoniously with the Earth and promotes good energies. But here are a bunch of reasons why this just isn't a valid argument. First of all, 440 Hz is also a multiple of 8 Hz, so what's the problem? Tuning A to a certain frequency doesn't make all your music resonant to something, only the A notes. What about the other notes and the musical scales that don't include the A note? Especially, the semitones close to A would still be very inharmonious with the universe or whatever. The Earth has a series of electromagnetic resonances known as Schumann resonances, and the first one is what they refer to as the 8 Hz resonance. However, the first electromagnetic resonance of the Earth is not exactly 8 Hz, but 7.83 Hz. So, 432 is not a multiple. And if we look at the frequencies associated with the water molecule or with human organs, we see that they have absolutely no significant relationship with the numbers 8, 256, or 432. Earth's resonance is electromagnetic, while sound is not electromagnetic but mechanical waves. But what is the difference? A sound wave is mechanical. That is, what vibrates is matter, so groups of atoms. Meanwhile, light is an electromagnetic wave. That is, what vibrates are electromagnetic fields, which are not matter. Sound cannot travel through space, but electromagnetic waves can. Another important difference is the wavelength. Just as a small reminder, light is a type of electromagnetic wave, so the speed of electromagnetic waves is simply called the speed of light. Electromagnetic waves have different wavelengths than mechanical waves, even for the same frequencies. This is because the speeds of sound and light are quite different. The speed of sound, dry air, 20 degrees Celsius, is 343 meters per second, while the speed of light in a vacuum is almost 300 million meters per second. For example, if we compare the wavelength of an electromagnetic wave and a sound wave, both at 8 Hz, we see that both wavelengths are in a completely different order of magnitude, by a factor of almost 900,000. And if the wavelengths of light and sound are different for the same frequencies, that means that the size of an object can match one type of wave but not the other. That is, something that resonates electromagnetically at a frequency is hardly going to resonate acoustically at that same frequency. Aside from the fact that sound waves are far too short to be a considerable submultiple of the Earth's diameter, the sound produced by a musical instrument, or even an orchestral ensemble, is so insignificant that it would not go far across the entire planet Earth, reflect multiple times, and interact with itself to produce a resonance. The spiritual community tends to assert that sound and light are fundamentally the same only because they are both vibrations, and that the only difference is that they are at different frequencies. So that, apparently, if you increase the frequency of a sound until you reach the frequencies of visible light, you suddenly get light. But we already saw that light and sound are very different, not only in terms of wavelength, but also in terms of what they are physically. This is a very clear example of when there is no real understanding of the physics behind natural phenomena, so they end up relating things that are not related to begin with. The only interaction that light and sound have is that the compressions and expansions in a sound field modify the density of the medium, which makes the speed and direction of light change very, very slightly. In fact, the interaction between light and sound was my thesis topic to graduate from my master's degree in acoustics. If you want to read my thesis, I will leave the link in the description, although it may be too advanced. Another common mistake is associating integer numbers, that is, numbers without decimals, to better and more harmonious frequencies. Here, it is very important to distinguish between mathematics and numerology, and to keep in mind that numerology is not at all significant in science. In some examples, they propose a tuning where the list of frequencies are only whole numbers. For them, this means that the numbers are more exact, and therefore more pure and harmonious. In music, however, the ratio between the frequencies is always perceptually more important than the frequency values themselves, because the frequency ratios are what produce harmonies. Forcing numbers to have no decimals will simply give you less harmonic proportions. There is this YouTuber called Adam Neely, a professional musician and academic, who also addresses this issue but from a more musical point of view. He simply tunes his keyboard to different A4 equals 432 Hz tuning systems, improvises, and comments on how it sounds.
So maybe we're targeting too many chakras at the same time?
His point is that to suggest certain frequencies and tunings for music, first one should try making actual music with them and know what they sound like. I highly recommend that you watch the original video and Adam's channel in general. Whether or not a number has decimals does not make it more pure or perfect. I give you the example of the legendary number pi. This number is irrational, that is, it has an infinite number of decimal digits and cannot be expressed as a fraction. But just because of that, are we going to say that pi is an ugly and imperfect number? No, pi is one of the most beautiful numbers that exist because it describes circles, which are a fundamental geometry of the universe. In fact, the sine waves that describe vibration phenomena are derived from circles. Some people modify commercial music to convert it to an A4 equals 432 Hz tuning. There is actually nothing wrong with this, especially since in this case they are preserving the equal temperament. In the end, it may be a simple matter of personal taste. But if they want to associate it with a better health or a better spiritual harmony, I would simply repeat everything I previously mentioned. Even Verdi himself, who once expressed some interest in tuning to 432 Hz, said so for purely practical reasons. At the time, the standard frequency of A4 was being repeatedly increased, and all Verdi wanted was for them to stop raising it, in order not to increase the strain on his opera singers, and his suggestion was to leave it at 432 Hz. But he never gave any esoteric reasons like the ones I've discussed. That's something people added later. Finally, I want to talk about tuning specifically a guitar to A4 equals 432 Hz. Putting aside the spiritual arguments, you actually can tune a guitar to 432 Hz tuning or whatever frequency, as long as the frequencies in the strings respect equal temperament. 440 is actually a number as arbitrary as 432, with the only difference that 440 is set as the standard. As a reference, these would be the frequencies to tune a guitar to A4 equals 432 Hz and equal temperament, with the strings tuned to the standard notes. However, let's recall that many of the A4 equals 432 Hz tunings on the internet use intonations other than equal temperament. These tunings would not work on a guitar, since this is an instrument specifically built for equal temperament. In episode 3 on musical frequencies, I mentioned the problem with just intonation tunings. In these tunings, the ratios between the frequency of a musical note and its next semitone are varying through an octave, while equal temperament is designed precisely so that the ratio between a musical note and its next semitone is exactly the same for all notes. But how do we know that a guitar is built for equal temperament? The frequencies of musical notes and the position of the frets on a guitar are related in the following way. The frequency produced by the string is inversely proportional to the vibrating length of the string. That is, if we start playing any musical note on the guitar, and we want to go up to the next semitone, whose frequency is the previous frequency times the 12th root of 2, then the next fret will reduce the vibrating portion of the string by dividing the vibrating length by the 12th root of 2. Again, let's recall that in equal temperament, the interval between two adjacent notes is always the same regardless of the note. Now, if we look at the guitar, it has straight frets that span all of the strings, marking the same positions for all the strings equally. Considering that different strings are tuned to different notes, that means that the guitar will be giving equal intervals for all the notes. Now, what happens when you tune a guitar with an intonation different than equal temperament? Let's use Pythagorean tuning as an example. When playing open strings, the frequency ratios will be of Pythagorean tuning. And like we said earlier, the frets on the guitar give you equal temperament intervals. Then, by pressing your fingers on the frets, you will be adding equal temperament intervals to the notes in Pythagorean tuning. So in the end, you will get intervals that are neither equal temperament nor Pythagorean tuning, but a strange mixture of the two. If you see a 432 Hz tuning and the frequencies for these notes are different, then it is not equal temperament, and therefore not appropriate for a guitar. To play with a different intonation, you need a guitar that is designed for that intonation specifically, and the strings will always have to be tuned to those fixed musical notes. Finally, I'll state again that this whole thing about alternative frequencies and tunings is completely acceptable from a perspective of personal taste. However, it is not correct to give physical and mathematical arguments without really understanding the physics and mathematics of sound. And it is also not correct to give arguments on physical or mental health without the appropriate scientific studies. And again, one should try making music with those tunings before claiming they sound better. With that, we conclude this video. See ya!